My name is Lori Milliken, and this lecture is about testing for differences between groups. Are the means different? So many research studies compare two or more groups rather than trying to quantify associations between variables. We already talked about correlations and regressions, and those are techniques used to determine how strong an association or a relationship is. However, there are many kinds of research studies where groups are being compared, and this is typically experimental research. So the question is there a statistically significant difference between the two groups? Now usually the groups are getting something different. One is maybe a control group and the other group is some kind of an experimental group. So the difference between groups for whatever outcome variable is being measured means that whatever that experiment was, it made a difference. And so the tests that we're going to talk about will be mainly t-tests and analysis of variance. There is something called analysis of covariance. I'll just mention it to tell you what it is, but we're going to really focus on the t-test and the ANOVA. So what factors are considered as we compare these groups? Well, first of all, how different are the groups? Remember that the value for one of the groups is the mean for that group. So the one number that you look for to describe that group, to describe the middle of that group, is the mean. And so we're going to be comparing means between groups. Is there a big mean difference between the groups? Are the means far apart, or are they really close together? That will make a difference in considering whether that difference is statistically meaningful. The other thing we're going to look at is what is the variability in each group. And so there's this idea of the partitioning of variance, meaning how is the variance within each group compared to between groups compared to the variance of the entire group altogether. And I'll show you a picture of this coming up. The last thing that is considered in these analyses is how many people are in each group. And the number of people, another way to look at that is called degrees of freedom. So you usually take the number of people and you minus 1 or 2 depending on the analysis you're doing, and that's called degrees of freedom. You won't be dealing with this directly. You'll probably see degrees of freedom maybe reported in research articles, but since you're not actively calculating these, you're not going to need to really deal with this much. If you go further in statistics and actually maybe carry out research studies, you will probably need to know a little bit more about this. So in general, here's what we're going to be talking about in this slideshow. We're going to be talking about a scenario where two groups are being compared, and these are going to be t-tests. So a t-test compares two groups. There is something called an independent t-test where the groups are unrelated, and there's another called a dependent t-test where groups are related, and I'll talk about this more a little bit later. If you have a research study design that has more than two groups, so 3 or more groups, you cannot use a t-test to compare those groups or the group means. You need to use an analysis of variance. And just like for the t-test, there are two different flavors of ANOVAs. One is a one-way analysis of variance, and in a one-way analysis of variance, this is typically where the groups are also unrelated, so very similar to an independent t-test. The other kind of analysis of variance is called repeated measures ANOVA. And so these 3 or more groups are usually the same people measured over and over again. And that's a situation that's very similar to the dependent t-test. So there is the t-test that you use for two groups, and it can be where the groups are related or unrelated. And when you have 3 or more groups, you have to shift to the analysis of variance, and there are dependent and independent versions of those two. So let's talk about these in a little bit more detail. So first is the independent t-test. This is a statistical technique used to determine whether two independent groups differ in a specific characteristic. So these independent groups are separate groups. They're made up of different people. The different people are unrelated. So this is an example of this might be a group of males versus females, or maybe a group of people who did not get a study drug compared to the people who did get the study drug. So someone in one group cannot possibly also be in the other group. So these are independent groups. This is an independent t-test. There are some assumptions associated with t-tests, and the assumption is that the samples are random, they're normally distributed, and they come from the same population. So this is important to remember. Remember that when a researcher does a study, they recruit people from a population. So they recruit a sample from a population. Then that sample is usually randomly divided into groups, and one of the groups gets something different than the other group. And so now you have a sample from the population that was divided up into two groups. And so those groups are from the same population, and the samples are random, and the data are normally distributed. The other thing is that the two groups should have a similar amount of variability, and so if you if you get a sample from the population, randomly divide them into groups, typically they will have similar variability. So you can look at the standard deviation of each of the groups for whatever variable you're measuring. So this is a scenario where you would do an independent t-test. The other kind of t-test is a dependent t-test. So this is a statistical technique. It's also used to compare two groups, but in this case the groups are dependent. They are related. So many times it's the same people being measured over time. So maybe someone is measured at baseline of the study, and then maybe 6 weeks later. It's the same person being measured and remeasured. And so you would use a dependent t-test to compare a group at baseline compared to where they are somewhere in the future, 6 weeks, 6 months. So if you're comparing two means of people who are the same people being measured and remeasured, then you would need to use a dependent t-test because the groups are related. Another example is, let's say we're going to measure the performance of students on an exam in a quiet room versus a very noisy room. And so you'd have, let's just say we're going to take a bunch of people and they're going to do the test twice, or an equivalent test twice. On one day they come in and they sit in a quiet room to take the test. On another day they come in and they take a similar test, but they do it in a very noisy room. And you're going to compare the score on the day that it was quiet to the day that it was noisy. And so in that kind of scenario, it's the same people being measured under two different conditions. So in that case, if you want to see if noise made a difference in someone's ability to take a test, then you would need to use a dependent t-test in that case because the groups are related. So a dependent situation is usually when you have the same group of people measured over time, and that's the comparison you're trying to make, or the same people being measured under different conditions. That's a dependent t-test. Similar assumptions as the previous test. The sample is random, normally distributed, so that still applies. So I want to talk a little bit about, give you a visual of what we're doing here. We're going to move into a discussion of analysis of variance. But before we do that, I just want to talk about the role of variability in these comparisons. And so just take a look at these three pictures. These are pictures with of low variability, medium variability, and high variability. In each of these pictures, there are two normal curves. So the green line and the blue line is each a different normal curve for a group of people. And so that's the distribution of two groups of people. So let's just say the green group got one kind of condition and the blue group got another kind of condition. So maybe we could just take that scenario we just talked about of the test taking in the quiet room versus the noisy room. So let's just say the green curve was the noisy room and the blue curve was the quiet room. And there is a mean difference being presented here. And the mean difference is being presented by that vertical dotted line. And you can see that I've lined up these three pictures so that the mean difference, you can tell right away, is the same in the condition of low variability, high, and medium variability. It's the same mean difference. The peaks of the curves are the same distance apart. And the peak of the curve is where the mean falls, right? So that those vertical dotted lines, that's the mean for the green group and the mean for the blue group. And they are a certain distance apart. And so in the example we're talking about here, the x-axis, the horizontal axis, is the exam score. Exam score in a quiet room, exam score in a noisy room. And so exam scores may differ under those two conditions, and that's what we're trying to test. And so we use these statistical tests to tell us if there is a significant difference between groups. And remember, significance tells us the error that we will make when generalizing the result from the sample to the population. If we get statistical significance, that means we're pretty confident that we can take the result from the sample and generalize it to the population. So we're doing this little study where we have a quiet room and a noisy room, and they're taking a test. In the case I described, it's the same people coming in on 2 different days under 2 different conditions. If we want to make the inference or the generalization that it's important to have a quiet room when you take a test, then we need to prove that there is a statistically significant difference between these two groups based on our study. Okay, so I just want to show you the impact of variability here. Now just take a look at the very bottom picture, the low variability picture. So you have two normal curves, the green and the blue, and in the low variability scenario, the data are very clustered right around that mean. So there's not a whole lot of spread in the data. And you can see that the two peaks, blue and the green, are quite separate from each other. There's not a lot of overlap. The variability doesn't kind of overlap, and there's not a lot of spread. And of course there's not, because this is a low variability kind of picture you're looking at. It'll be easier to say there's a difference between the blue and the green groups when you have low variability, like in that bottom picture. Compare that to the middle picture of very high variability. So maybe there's a big spread in the scores of on that exam in these groups. Because there's so much overlap in the curves for these two groups, it'll be, from a statistical standpoint, very difficult to say there's any difference between these groups in that high variability scenario. So I just want to show you that just because there's maybe a big mean difference doesn't necessarily mean that there is a statistically significant difference, because you might have a lot of variability. So these statistical tests not only consider how far apart these two peaks are, but they have to consider how much variability there is there too, to determine whether it's statistically significantly different. So let me just tell you that you might have a case where you're looking at high variability. There's a certain mean difference, but there's too much variability to be absolutely certain that these two scores, average scores, are different. And so if you do not get a statistically significant result from a t-test, for example, for all intents and purposes, these means are the same. So probably in the high variability scenario, if you did a t-test just based on that picture, you would probably get no significant difference. And from a statistical standpoint, that means that these blue and green curves are essentially the same, statistically speaking. And you'll see that in some of the articles that we end up looking at. You'll see that the means may not be exactly the same number. They may be different by a little. But the question is, are they different enough to be statistically significantly different? And whenever I ask a question, are the means different, we're always talking about, are the means significantly different? Okay, here's an example this is one of our practice articles that you'll see in this course. In this study, it was kind of a neat little study. They restricted opportunities to be active during the school day. This was a study done out at an elementary school in Arizona. And the researchers went into the school, and on one day, they made all of the kids stay indoors all day long. They couldn't go out to recess. They didn't have PE that day. They had to eat their lunch and then stay inside. They couldn't go out onto the school playground. And really what the researchers wanted to see was whether the kids made up for that lack of activity during the day by being more active at the end of the day, after school. So did the kids who were all cooped up all day, once the school bell rang, did they run outside and be really, really active because they were cooped up all day? Or did they remain kind of sedentary? And they compared that to a condition where they went to the same school, just on a different day, and the kids were allowed to go out to recess. They were allowed to have PE, and they were allowed to eat lunch and then go out into the playground. Okay, so what you're looking at on the screen is a graph of movement counts per minute. So they had the kids wear these little devices called accelerometers. It measures movement, almost like a pedometer that measures steps, but in this case it measures how much and how intensely you move. It's a little device you wear on your belt. And so these are movement counts per minute. On the x-axis is time during the day, 8:30 in the morning, 9:30 in the morning, etc. And then the open circles are the active day, and the black triangles are the restricted day. Now don't forget, these are the same kids being measured on two separate days. One day they were allowed to be active, the other day they were restricted in their activity. So just based on that, there are two conditions being compared, active and restricted. And so if there are two conditions being compared, that is a t-test. So this has to be a t-test because there are two conditions. And because, in this case, it's the same people in both conditions, so it's the same kids being measured on the active day as were measured on the restricted day, this is dependent. So this is an example of a dependent t-test. So you can read through this article will be posted on the website. You can read through some of this if you'd like, but let's just draw your attention to Table 2. And so they wanted to look at these movement counts. How much did they differ? And they broke it up by time period on the left-hand side. And at the bottom row, they give you the total day. They give you the mean and standard deviation for these movement counts on the active day, and the mean and standard deviation for the movement counts on the restricted day. And so, for example, during the school day, 9 a.m. to 3 p.m., on the active day, the kids had 366 movement counts plus or minus 165, which is the standard deviation. That's on the active day. On the restricted day, they had 129 movement counts plus or minus 85. And the last column gives you the p-value, the level of statistical significance. Remember, anything less than 0.05 or 0.05 or less is statistically significant. So this difference between the active day and the restricted day was statistically significant because the p-value is less than 0.05. Well, this kind of verifies the fact that, yes, they did manipulate activity. They allowed kids to be active on one day and then they restricted them on the other day. So did that restriction work? Yes, it did. There is a statistically significant difference between the active day and the restricted day in their movement counts. 366 on the active compared to 129 on the restricted. You can also just go down the line and look at each of these other time points. During recess, during lunch, and during physical education, you'll see the p-value is very, very small, a bunch of zeros. Actually, if you were to carry out those digits of the p-values for recess, lunch, recess, and physical education, it says 0, 0, 0, but if you carried out those digits, you would see that it would be a very small decimal point, but they just don't carry it out. So the p-value is very small, meaning there is a statistically significant difference between the active and the restricted day in movement counts for recess, lunch recess, and physical education. Now, the after-school period. This is the one that's most interesting. Will the kids who are restricted, with all that cooped up energy, will they run out the doors and be active because they were cooped up all day? Or will the after-school period differ at all for movement counts? So let's see what happened. After school from 3 o'clock to 7:30 p.m. on the active day, there were 525 movement counts for that group of children. On the restricted day, they had 246 movement counts, with a p-value of 0.012. That is statistically significant. What's very interesting is that on the active day, so they were active at 3 points of time during the day, recess, lunch recess, and PE, and then after school they were still more active than the restricted day. So on the restricted day they weren't allowed to do anything, and they left school very lethargic, and they didn't do anything after school either. There was a significant difference in movement counts. Very interesting. So so this is an example of a research study that had two groups being compared, or two conditions, active versus restricted. And in this study they looked at movement counts. That was the outcome variable. And they looked at movement counts and chunked up into various pieces of time here. But it was always active day versus restricted. And they gave you a p-value. So this is an example of a t-test because it had two groups, and it's a dependent t-test because the groups were the same kids being measured and remeasured. And if you take a look at the paragraphs describing their analytical test, you'll see the second paragraph. It says dependent t-tests were used to verify that active versus restricted manipulation of activity during school resulted in significant differences. And so there you go. It tells you what test that they used. So this is an example of a t-test, two groups. So let's now talk about analysis of variance. This is a statistical technique used to determine whether more than two groups differ in some specific characteristic. Again, it can be a situation where the groups are independent, called a one-way analysis of variance, or a situation where the groups are dependent, and that's called repeated measures. Very similar assumptions as what you've already seen. Samples are random, normally distributed, and come from the same population. You need to see if the variability between groups are similar. And typically researchers will test for that, and you can make an adjustment if the variances are, or the standard deviations are different. I just want to mention briefly something called analysis of covariance. You might see that out in the literature. Analysis of covariance is an analysis of variance that has a little extra step added. You covary out baseline scores. So you can adjust statistically for differences that might be present at baseline. And so sometimes this is used, and you'll see it out in the literature. It is essentially an analysis of variance where they use it to adjust for baseline differences. So if you have a situation where you cannot randomly assign groups, or even after your random assignment because some fluke or something happened where your baseline scores are different, so even before you apply the treatment, your groups are already different, you can adjust for that statistically, and you use an analysis of covariance to do that. And you need to do this because sometimes the amount of change you see over time is affected by where people start. This is a very classic situation that happens in exercise training studies anyway, because sometimes you take a more fit person and you have them do an exercise program, you're not going to see much change. But you take a very sedentary person, you put them on an exercise training program, you're going to see them change by a lot. And so sometimes you need to adjust for these baseline differences. One thing I just want to mention, you might see in research papers something called a post hoc test. Okay, so a post hoc test comes after a analysis of variance. So remember, the analysis of variance is a comparison of 3 or more groups. Now what happens is, when you do an analysis of variance, which no one does by hand anymore, you have your computer do it for you, the analysis of variance tells you that there is some difference, or not, between the 3 groups. But it doesn't tell you specifically which groups are different. So let's just say you had 3 groups. Your analysis of variance would give you one p-value that tells you whether there is some difference between groups. It doesn't tell you if it's different between groups 1 and 2, or 2 and 3, or 1 and 3. To get that information, you need to do a post hoc test. So this is used after the analysis of variance, if the analysis of variance showed that there was a significant difference somewhere. So the ANOVA shows whether you have a difference somewhere, but it doesn't tell you specifically which means. A post hoc test will tell you specifically which groups are different. So you might see that mentioned in the literature. Typically researchers will describe what kind of analysis of variance they used, and there are many different post hoc tests. They'll tell you what kind of post hoc tests they used in their analysis. So let me just talk a little bit about this idea of analysis of variance. Because you might be thinking, well, why are we analyzing variance when really you said this is used to compare means? If you're comparing means, why are you analyzing variance? Okay, so let me just talk about that for a second. And at the beginning, I also talked about the fact that I used the words partitioning of variance. And so let me talk about what this means. So here's the scenario. We have a population. We have, you can think of this as 3 samples from the population, or you can say, you can draw 1 sample from the population and then randomly assign to 3 groups. Either way, it's the same because it's all random. Okay, so you end up with these 3 groups. And let's say, I don't know, I'll make something up. Sample 1 is going to be the control group. Sample 2 is going to get the fancy-dancy new cholesterol-lowering drug at a low dose. And sample 3 is going to get the fancy-dancy new cholesterol-lowering drug, except it's going to be at a high dose. So you have control group, they get a sugar pill or some kind of placebo. Sample 2 is the group that gets the low dose of cholesterol drug, and sample 3 is the higher dose of drug. So don't be scared by this picture. Let's just say that along the x-axis we have our 3 groups, groups 1, 2, and 3. Along the vertical is the DV stands for dependent variable. In this case it's cholesterol. So we're going to put these people on their different pills. The group 1 is the placebo pill, the group 2 is the low dose pill, and the group 3 is the high dose pill. And we're measuring what their cholesterol does after being on this pill for a period of time. So the dependent variable is cholesterol. So we could have made the scale for the numbers of cholesterol. So what you have here is you have 4 people in group 1. This is just kind of a schematic to kind of show you what might happen. So you have the 4 people in group 1. They're labeled X11, X21, X31, and X41. So 4 people in group 1. Then you have 4 more people in group 2. Then you have 4 more people who are in group 3. These are the 3 samples. If you look at the mean for each sample, you can calculate the average for group 1, the average for group 2, and the average for group 3. And that's represented by the blue X's. But you also have to understand that there's variability around each of those X's. Okay, so there is a certain spread of scores around each of those means. So we could have had this so that the 4 X's were really spread apart by a lot, or really clustered even more. You also can, because these are 3 samples from the same population, you can calculate an overall mean of the whole group. So take all 12 people, calculate an overall mean. That number is the green X with a line on top. That's the symbol for a mean. So that's the overall mean. You have each group mean, but you also have variability within each group. And again, since there is since these are 3 samples from the same population, here's why it's analysis of variance. If these are 3 samples from the same population, and if the groups were not any different, you could look at the overall amount of variability, and it should be very similar to each individual group's variability. So you have each group mean and its variability, so a mean plus or minus a standard deviation. And you can compare that to the overall group mean, so the green X, and its standard deviation. So the overall group, all 12 people combined here, has a mean and a standard deviation. If the groups 1, 2, and 3 are different, you're going to see that the overall standard deviation of the entire group is going to be a bigger standard deviation. There's going to be more variability if these 3 groups are different. So just take a look at the picture. Group 3 seems to have a higher average than groups 1 and 2, just visually taking a look at that. If it didn't, let's say groups 1 and 2 were where they were, and group 3 was lower, about the level of where group 1 is. Can you see that the overall amount of variability, the overall spread in the scores will be smaller compared to where group 3 is right now? So if you look at the overall variability for the green X, you have the X from group 1, the 4th person down there, and the 4th person for group, the 1st person for group 3. You can see there's a wide range of scores when you consider all 3 groups combined. If you compare the variability between the groups to the variability of all 3 groups combined, you can tell something about whether the groups show any differences. Okay, so if these groups were not different, your variability for each group would be a very similar variability as the whole group combined, so the 3 groups all combined together, because these are 3 samples from the same population. When you have one group or more than one group that's different than the others, you're going to affect the overall variability of all groups combined. So the variability of the green X is going to get bigger and bigger as the groups become more and more different. And that's why this is an analysis of variance. You analyze the variability. Because if the 3 groups are from the same population, and if the groups are not different, all the variability should be the same. The variability for X1 should be the same as X2 and as X3 and as the whole group combined, the green X with its variability. As these means become more and more different, further apart, the overall variability is increased. And when the overall variability gets really big compared to the small variability per each group, that must mean you have a mean difference somewhere. So just picture group 3 being even higher. Maybe they're up at 40 instead of 20. So they're really high. As group 3 values get really, really high, the variability for the green X, the overall mean, is going to get bigger and bigger. And that must mean you have a mean difference if the individual variability of groups 1, 2, and 3 is the same, but very different from the overall variability. So this analysis ends up being an analysis of variance. Now you won't be calculating this by hand. If you ever calculate this, it'll probably be with a computer. But for you, you'll be reading the literature of the results of this. And so you don't need to know how this is done per se, but you need to know that this analysis can compare 3 or more groups. It's called analysis of variance. It's going to give you a p-value that tells you whether there's a statistically significant difference. The post hoc test will tell you which specific groups are different. So in this picture, just looking at it visually, it looks like group 3 has a higher score than the other 2 groups. So the analysis of variance will probably come out with a p-value that is significant. And a post hoc test would tell you, well, which of the groups are different from which. Is 1 and 2 different? Well, they're pretty close. I don't know if they're going to be different. 1 and 3 probably are different. 2 and 3, they may or may not be different. So your analysis would tell you that. And so the post hoc test gives you the individual group differences. Here's an example of a study where analysis of variance was used as the method to analyze the data. And so in this case, this was the comparison of 1 versus 2 days per week of strength training in children. And these both were compared to a control group. So there were kids that did not train, other kids that came in 1 day a week to train, and other kids that came in 2 days a week to train. The outcome measures there were 2 of them. Well, if you actually read the paper, there were more than 2, but in Table 2, there are 2 outcome variables being shown. One is the strength on the chest press machine, and the other is the strength on the leg press machine. Again, 3 groups, control 1 day, 2 day. These kids were measured at baseline and measured after the 8 weeks of training. But what was compared here was the change from baseline to post-training. So how much did strength increase or not over the course of the training? That's what was compared between the 3 groups. And you can see that at the bottom of the table it says the change in strength from baseline to post-test, significantly different from control. So they give you a little symbol that tells you which groups were different from the control group. So the kids who didn't train, let's just look at chest press, they started out at around 18.2 and they ended up at the end of the study at 19. Teeny weeny increase. Kids, even if they don't train, they're probably growing, and so they might get a little stronger just from growth. So there was a small increase. The 1 day group also increased from 22.3 to 24.3, and the 2 day group started at 21.7 and ended at 24.2. Then the researchers do their analysis of variance to compare these 3 groups, control versus 1 day versus 2 day, for the amount of increase in strength for the chest press. Did the amount of increase in the chest press differ between control, 1 day, and 2 day? So those are 3 means: the change in strength, chest press, control, 1 day, 2 day, means it has to be analysis of variance, because there are 3 groups. The kids in the control group were different kids than the kids in the 1 day group, who were also different kids than the kids in the 2 day group. So these groups are independent. So this is a one-way analysis of variance. If you look at the last column, it gives you the p-value. There's a star right next to the p-value, and it says this significance level is from the analysis of variance. So in both of these analyses, chest press and another for leg press, there was statistical significance in both of these from the analysis of variance. But then they had to do a post hoc test, and you can take a look in the paragraph here, about 3/4 of the way down. They say 2 key post hoc tests were used to identify specific group differences. So 2 key is a type of post hoc test, presumably named after a guy named Tukey. So they did the analysis of variance, and then they did post hoc tests to see specifically which groups were different. And for the chest press, the 2 day group was different from all the others. I'm sorry, the 2 day group was different from control group. That's what they say in their footnote. There's a little symbol at the end of the row of data for the 2 day group for chest press. Right after the 7.7, there's a little symbol there that matches the symbol in the footnote. That symbol means that that group was different than the control. The 1 day group, there is no symbol next to the 1 day group, meaning that the 1 day group was no different than the control group. So the change in strength in the 1 day group was not statistically significantly different than the change in strength in the control group. It took 2 days of training per week to be significantly better than either 1 day or control. The leg press was a different story, so now you're looking at the bottom half of the table. Same kind of setup, control 1 day, 2 day, except now we're measuring the strength of the legs. So here's the other analysis of variance that was done. The p-value from that one came out to be 0.009, so that's significant too. And then they specify which groups were different. And so in this case, for leg press, there's a little symbol on the row of data for the 1 day, and there's a symbol for the row of data for the 2 day. So this means that the 1 day group was different than the control, and the 2 day group was also different from the control. So it didn't matter if you trained 1 day per week or 2 days per week, they both resulted in significant increases in strength compared to the control group for the leg press. For the chest press, for chest press strength, you needed to train 2 days a week. 1 day a week was not enough to get you above what you would get if you did nothing. So this is an example of a study where there are 3 groups. In this case, these were independent groups. And this is an analysis of variance followed by a post-hoc test. And one thing I'll say about interpreting these kinds of studies is that I would read very carefully the title of the table, the footnotes of the table, the labels of the columns and the rows. Find those stars or asterisks or whatever symbol they use to highlight what's significant. So you'll need to make sense of all of those symbols in these tables. So this was analysis of variance. Okay, so now I want to walk you through some examples because I know it can be hard to start getting the hang of which statistical test should be used in which kind of study. So let's go through some examples. So let's take the scenario where we're going to look at the effectiveness of a couple of different weight loss programs. And so we want to determine whether a program that has intensive psychotherapy plus diet and exercise, to see if that's any more effective than a traditional diet and exercise program for long-term weight loss. And so presumably we're going to recruit a sample of people, randomly assign them to 2 groups, the traditional diet and exercise, and then the same diet and exercise program plus the intensive psychotherapy. So we're testing the effectiveness of psychotherapy added to the diet and exercise program. Okay, so both groups have diet and exercise, and only the one group has psychotherapy on top of it. So we are going to be comparing how much weight ends up being lost at the end of, let's say it says long-term weight loss, let's say 1 year. At the end of a year of diet and exercise for both groups, and one of the groups gets psychotherapy. We're going to look at the amount of weight lost at the end of the 1 year between these 2 groups. What statistical test would be used? This is going to be an independent t-test. It's a t-test because there are 2 groups. We're comparing diet and exercise to diet and exercise plus psychotherapy. 2 groups. It's independent because these people are unrelated. The people in the diet and exercise group are different people than the people who are also getting the psychotherapy. These are unrelated groups. The variable that's being measured, the outcome variable, is weight loss. You could probably measure a whole bunch of other variables too. If we drew blood on these people, we could measure cholesterol. We could measure blood glucose. We could measure a whole bunch of things. For each of those variables, you would perform a t-test. Is cholesterol different between the 2 groups? Is weight loss different between the 2 groups? Each of those analyses would be a separate independent t-test. Example number 2. Now we're going to look at whether a community-based weight management program reduces sedentary behaviors and increases physical activity in girls. So let's just focus on one of these. Let's say, can this weight management program increase physical activity in girls? So we're going to measure activity. And, well, since we're going to be putting them on a program, we should measure their physical activity before they start the program, and then measure it after they're done the program. So let's say we're going to recruit girls at a YMCA, have them participate in this 12-week program. We're going to measure various things like weight and sedentary behavior and physical activity level before they participate in the program and when they finish the 12-week program. So if we want to compare whether they improved in these variables from baseline to 12 weeks, what statistical test would it be? Okay, so you have a value for weight at baseline and a value for weight at 12 weeks. If you want to see if weight changed between baseline and 12 weeks significantly, you need to do a t-test because it's 2 time points, baseline and 12 weeks, for weight. Also, because it's the same people at baseline as are at 12 weeks, it's going to be a dependent situation. So if you want to compare weight at baseline to 12 weeks, it's going to be a dependent t-test to determine if weight significantly changed. You can do another dependent t-test on physical activity level. What was the physical activity level at baseline? Did it change at the 12-week mark? That comparison between baseline and 12 weeks for physical activity level is going to be another dependent t-test. You could do sedentary behaviors. You could measure hours that they spend being sedentary at baseline and then repeat that measurement at 12 weeks. The hours spent being sedentary being compared baseline to 12 weeks, 2 time points, the same people being measured and remeasured. It's another dependent t-test. So for every outcome variable that you measure in the study, and you're comparing baseline to 12 weeks, that is a dependent t-test. Example number 3. Let's see if a new drug to treat diabetes is effective and what that minimal effective dose is. So we're going to recruit a sample from a population, and we're going to randomly assign people to the following groups: placebo, low dose, medium dose, and high dose. So we have 4 groups here. One group that's getting no active ingredient in their pill, another that's getting a low dose, then a medium dose, and then a high dose. 4 different groups. Let's say they are in the study taking their medicine for a period of time, 1 month, 2 months, whatever it is. At the end of the study, we're going to compare these 4 groups. Whose diabetes was better? We can do a glucose tolerance test and take the results of that and compare it between the placebo group, the low dose, medium dose, and high dose. What statistical test is that? Well, it's 4 groups, and so you can't use a t-test anymore because a t-test is only for 2. So it has to be some sort of analysis of variance. Now the question is, for this analysis of variance comparing 4 groups, is it an independent or dependent situation? Okay, well, these people in the groups are separate people. They're unrelated. The people in the placebo group are not the same people as the people in the low dose, medium dose, or high dose groups. So these are independent. So this is called a one-way analysis of variance. It's the independent version of analysis of variance because the people in these 4 groups are different people. And here's the last example. Let's see whether there is an effect of music on aerobic performance during a stress test on a treadmill. So we're going to get a group of people and have each person perform a treadmill test. And they're going to do it 3 different times in 3 different conditions. So one time they're going to come into the lab and they're going to run on the treadmill with no music playing. Then on another day, maybe separated by, let's say these 3 trials are separated by a day. So we're going to come in on Monday and do 1 trial, no music. Then on Wednesday they're going to come in and they're going to do the next trial, run on the treadmill during slow music. Then on Friday they're going to come in and run on the treadmill in the last condition, which is fast music. You can even randomize the order in which each person does these tests. So the first person comes into the lab, they pick out of a hat one of these conditions and they do it on Monday. So each person is asked to do each condition in a random order. And what you're going to do is you're going to measure how long they stay on the treadmill during this maximal stress test. So the time, max time on treadmill, gets compared between these 3 conditions: no music, slow music, and fast music. So does fast music really make you perform better? Okay, that's the question we're trying to answer. If the max treadmill time is different between groups, there must have been an effect of the music. So because there are 3 groups, you can't do a t-test. You have to do analysis of variance. And because the people who were in the no music group were the same people in the slow music group, and they were the same people also in the fast music group, because they were the same people coming in multiple times to the lab and getting measured and measured with the same test but under different conditions. This is a dependent group kind of scenario. So what this is called for an analysis of variance is repeated measures analysis of variance. This is a repeated measures analysis of variance. So those are 4 examples just showing you the 4 different tests that we're going to talk about in this class. 2 of them were t-tests, independent and dependent, and 2 were analysis of variances, also independent and dependent. So here they are in summary. When you compare 2 groups or 2 means, the mean from each of 2 groups, you're going to do a t-test. You're going to do a t-test for each outcome variable that was measured. If the groups are unrelated, it's going to be an independent t-test. If the groups are related, whether it's under 2 different conditions or the same people being measured and remeasured, for example, if the comparison is baseline compared to a follow-up score, that's a dependent t-test. If you have a research design where 3 or more groups are being compared, then you have to use an analysis of variance. It's a one-way analysis of variance if the groups are independent. And it's a repeated measures analysis of variance if the people in the groups are being measured and remeasured, whether it's under different conditions, slow music, fast music, no music, or if it's a group being followed over time, baseline 6 months, 1 year. Did people change from baseline to 6 months to 1 year? That's 3 different time points being compared, but the same people being measured and remeasured. That's repeated measures.